Welcome to Chemistry 2, Unit 3, Thermodynamics. This is Lesson 3, Video 1. So we're going to put a lot of pieces together in this lesson. So we're going to talk about how delta H and delta S relate to one another with spontaneity. So we're going to be able to predict whether a reaction as written is going to just occur, be spontaneous or not, and if there is a specific temperature range at which it might switch from its spontaneity. So we're going to use something called delta G to calculate this. And this is called Gibbs free energy. And its symbol is a capital G. You might have seen this. It's the last column in your purple thermodynamics packet. And what this is defined as is it's the energy available in a system to do useful work. So after all the mechanics of bonds being broken, entropy being either taken away or added, it's what amount of energy is available to give off or the amount that's needed to be taken in after all the mechanics are done. The units are kilojoules per mole. And again, if we have the little delta G prime symbol, it's at standard conditions, and that's what your values in the chart are. They're at 25 degrees Celsius. So knowing the sign of delta G, the change in Gibbs free energy, that can be calculated, gives us whether or not a reaction is going to be spontaneous or not spontaneous. So we're going to have three scenarios. Delta G is greater than 0, which means it's positive. Delta G is less than 0, which is negative. And on occasion, delta G is equal to 0. So if we get a positive Gibbs free energy change when we calculate it, that means that the reaction is not spontaneous. If it's negative, the reaction is spontaneous. And if it's delta G, we are at equilibrium. And this is going to be a useful thing for when we calculate temperature ranges, because this is going to be the point at which it's not spontaneous or spontaneous. This is where it switches between the two. So we have different ways that we can calculate delta G. The first two, same thing as delta H and delta S. So we can use the summation equation and the packet. So we have products minus reactants, just like we did for enthalpy and entropy. We can use Hess's law again. And we have an equation that relates delta H and delta S with the temperature to calculate delta G. And that equation, you need to know this equation. It is really important. Delta G is equal to delta H minus T delta S. So we have to know what each one of these stands for. Delta G is our Gibbs free energy. So this is calculated. And then we can look at this chart to see whether or not our reaction is spontaneous. So this is in kilojoules per mole. Delta H is our enthalpy change. The units on this have been kilojoules per mole. T is temperature. And it must be in Kelvin. So you have to change it. So if you're given a Kelvin temperature, or degrees Celsius, it's degrees Celsius plus 273. And unfortunately, if you're given Fahrenheit, which I think you are in one problem, degrees Celsius is equal to 5/9 times the quantity, degrees Fahrenheit minus 32. So you might have to convert that. Delta S is our entropy value change. And the units on here mess everything up. So our units are joules per mole Kelvin. So big note here, very important. Divide by 1,000 to give us kilojoules per mole Kelvin. So we have to take our delta S value and make sure that it's in kilojoules, not joules. So if we look at our next page talks about predicting spontaneity. So on occasion, if we know the values for delta H, delta S, we can calculate what delta G may or may not be just by signs, and we're going to have conditions in which they are spontaneous or not. So our next video is going to go over this chart.